Hello mathematicians, we're now going to have a look at the derivative as a limit. Now we're still talking theory at this point. It's important theory, so it's worth the time to be spent on it, but we'll find easy ways to do this later on. So for the derivative as a limit, we're going to use the fact that for a curve where the gradient of the tangent varies, so we're not talking a straight line anymore, the process of finding the slope of the tangent involves a limiting process on the slope of the secant. Now we just had a very quick look at that on a previous GeoGebra, but just to refresh your memory, here we have the tangent passing through point A. We can see the slope of that tangent is 0.21. We've got a secant, so a short section of straight line joining 2 points on the curve. The slope of that secant is currently 0.55. You can see that it has a greater slope than the tangent. But as we get this secant and bring it back towards the tangent, the slope of the secant becomes a better approximation of the slope of the tangent, and eventually, when they are one and the same point, then the slope of the secant and the slope of the tangent are the same thing. Now that's the concept behind differentiation, which we're going to try to put some maths around. Let's have a look at the picture of the maths before we actually do it. So we're going to talk about the point that we are interested in finding the slope of the tangent at as point P. Instead of being x and y, we'll just call it x and f of x. We know that that's how you calculate y. And we're going to look at the point at the end of the secant, and it's a little bit further on in terms of the x value. So it's h further on, so it will become x plus h, and its y value will be f of x plus h. So the slope of our secant is y2 minus y1, f of x plus h minus f of x, over x plus h minus x. And as we saw, the slope of that secant has to become closer and closer to the slope of the tangent as the 2 points get closer together. So we want a way of describing the bringing together of these 2 points so that eventually they touch each other, they're one on top of each other, and the slope of the tangent is equal to the slope of the secant. So that's what we're going to develop the maths around. So here is that picture in words. So if P is a point on this curve, and Q, a little bit further away from X, so a slightly different value of Y, is any other point on the curve, doesn't matter whether it's to the left or the right, even though our picture was on the right, then the gradient of the secant, a straight line between P and Q, is y2 minus y1 over x2 minus x1. But of course, when we take x2 minus x1, that's x plus h minus x. And that's going to give us h on the bottom. Now, we want to bring those 2 points closer together, so that means that we want to take h to 0. And we know that the description for moving Q as close as we like to P is that we take the limit as h tends towards 0. So the gradient of the tangent is related to the gradient of the secant. So this much was the gradient of the secant. And the gradient of the secant becomes the gradient of the tangent as h tends towards 0. So that's our definition of the derivative. Actually, that's missing something there. That should say f dashed of x equals the limit as h tends to 0 of that. So this process is called differentiation from first principles. And again, differentiation from first principles is a tedious but important process. It's not the process we'll use unless we're particularly instructed to, but for the moment, we'll get our head around the concept. So let's consider this function, 5x squared. Now we know what that is. It's just a parabola passing through the origin, so vertex at the origin, and it's fairly steep-sided, or narrow if you like. So let's find f of x plus h. So f of x plus h, we know how function notation works, that if this is what f of x is, if f of x is 5x squared, f of x plus h means that we put x plus h in place of x in our original function. So that will become 5 times the square of the first, 5 times twice their product, and 5 times the square of the second. Hence, find this bit. So find f of x plus h minus f of x. So that equals 5x squared plus 10xh plus 5h squared minus 5x squared. Now generally, if we do this process correctly, the f of x will always cancel out with something in the first part. Part C then says, so this is building up our expression for f dash of x. So part C says, show that f of x plus h minus f of x all over h equals that thing. So we've just worked out what f of x plus h is. It's minus f of x. It's 10xh plus 5h squared. When that's all over h, if we take h out as a common factor from the top line, so if we set it up with brackets, h outside of 10x plus 5h all over h, then we can cancel those h's. So we get 10x plus 5h. Part D here finally gets us to do the differentiation, or to get the derivative. So we know that f dash of x equals the limit as h tends towards 0 of f of x plus h minus f of x over h. We've worked out f of x plus h minus f of x over h to be 10x plus 5h. So that's what we're taking a limit as h tends to 0 of. And when we do finally take the limit, it means we just substitute 0 where h is. So that will just give us 10x. Now, that then is the derivative. What's the significance of that? This is an equation for the slope of the tangent, which is the same as the slope of the curve, anywhere on our curve. So in part E, substitute x equals 1 into f dash of x to confirm that f of 1 equals 0. So let's just do that. F dash of 1 equals 10 times 1, which is 10, which means that when we get to x equals 1, so let's slide back up to our parabola here. When we get to x equals 1, which say it's around there somewhere, then the slope of the tangent is a fairly big number if this was drawn to scale. So it's 10. More interestingly, let's have a look at f dash of 0, because we know that 0 is this point here, and we know that the tangent is horizontal there. So f dash of 0 is 10 times 0, which is the slope of the tangent. And maybe also think about minus 1. If we took f dash of minus 1, that would be negative 10. So it indicates the slope of the curve out this side. So the derivative gives us an expression or an equation for the slope of the curve anywhere at all. And to find the slope at the point we're interested in, we put the value of x that we're interested in. So this process that the question has guided you through is, again, differentiation from first principles. We usually start at this point and just substitute in. Okay, for our next example, consider this function. It's always good if you know what the function looks like, which we do. X squared plus 2 is our parabola just there. And we're going to just combine these two steps here. We're just going to essentially say we want to find the expression for the derivative. So that is the limit as h tends to 0 of f of x plus h minus f of x all over h, which is the limit as h tends to 0 of, so f of x plus h is when we put x plus h where x is, so it's x plus h squared plus 2, minus f of x, which is x squared plus 2, be really careful with brackets, and that's all over h. Now we just do algebra. So we want the limit as h tends to 0 of, so we've got square of the first twice their product, square of the second, plus 2 minus x squared minus 2, sort of our double check that the original f of x goes. Next step is to actually get rid of this h on the bottom, because we know we can't put 0 into there or it will be undefined. So generally we can take h out as a common factor. So if we took h out as a common factor of what's left up here, we get this. So we want the limit of 2x plus h as we tend towards 0, which is just 2x. So again, what's the significance of that? It's the slope of the tangent and therefore the slope of the curve anywhere. So at x equals 0, which is here, the slope is twice 0, it's 0. And at x equals 3, which is out here somewhere, the slope is 6. So it all fits. I'm going to give you a little bit of hope for the future, in that we don't have to do this all the time, but we do have to know how to do it. And that is that in future, to find the derivative, we'll work the pattern which I'm sure some of you have picked up already. So when this was the function, the derivative was 2x. So x squared plus 2, we got 2x. When this was the function, 5x squared, we got as our derivative 10x. So 5x squared became 10x. Now when this is our function, I'm going to tell you, some of you, as I said, probably already know, that the derivative of this is going to become 2x plus 6. So I'm leaving it to you to actually go through and from first principles and show that by using our expression, the limit as h tends to 0 of that. But down the track, this is all that we'll be doing. We'll be using a shortcut. Till then, let's bed this process in by working these questions out of 7b. Remember what it is you're trying to do.